Imagine this. A pilot pulls back on the stick, trying to climb, but the plane just doesn't respond. Now that sounds terrifying, but what if it's not a failure? What if it's the invisible hand of software stepping in to save the flight? It's possible because today, the pilot's controls aren't connected by steel cables anymore, but by something way more complex. And that quote, it just hits you, right? It's the core of modern aviation. What used to be a very direct, very physical link, a system of actual pulleys and cables, is now all digital logic. A pilot's command isn't an order anymore. It's more like a request that the software has to interpret before anything actually moves.
So that begs the big question, doesn't it? Who is actually flying the plane? This massive shift from mechanical muscle to a digital brain has created this totally new and fascinating dynamic in the cockpit. And it's something that has been engineered and honestly debated for decades. Okay, so our story really kicks off with this incredibly gutsy experiment back in the early 1970s. The space race was in full swing, and NASA had these unbelievably advanced computers. So they decided to see if that same tech, the stuff that went to the moon, could actually fly a fighter jet.
This was a huge gamble. I mean, they literally ripped out the physical flight controls from this F-8 Crusader and plugged in the Apollo guidance computer. This was the first ever digital fly-by-wire system with absolutely no mechanical backup. If that code had a bug, the pilot was basically just a passenger.
So, how in the world do you measure if an experiment like this actually worked? Well, you ask the pilot. And this is what they use, the Cooper-Harper scale. It's the gold standard for rating how a plane feels to fly. A 1 is perfect, a dream. A 10 is, well, it's completely uncontrollable. The sweet spot, the really good zone, is anything from 1 to 3.
And here it is, the results. This is straight from the original test report. During takeoff, probably the most intense part of the flight, the pilots gave the system a 2. Not just flyable, not just okay, but good. The Apollo gamble had paid off, big time. It was official. Code could fly.
And this success, it changed absolutely everything. Designers were suddenly free. They could create planes that were aerodynamically unstable, which sounds bad, but it actually makes them incredibly agile and efficient. Modern jets like the F-35, they literally can't fly without a computer making constant, tiny corrections, something like 80 times every single second. No human could ever do that.
All right, so once the tech was proven, the commercial airline world had a whole new problem to solve. Now that a computer was basically a co-pilot, what should its relationship with the human pilot actually look like? This led to two very different schools of thought.
So you've got these two giants, Airbus and Boeing, and they took completely different paths. Airbus went with what's called normal law. Think of it as putting the computer in charge of safety. It creates these hard limits, a protective bubble that the pilot physically cannot push past. Boeing, on the other hand, went with soft limits. They believe the pilot should always have the final say. The system gives you warnings, you'll feel resistance, but you can always push through if you decide you have to.
And this quote right here, it just sums up Boeing's entire approach perfectly. The system is your trusted advisor, right? It's not your commander. It'll make it harder to do something dangerous. You'll literally feel the stick push back against you, but it fundamentally believes that the human in the cockpit has to have the final word.
Okay, so this brings us to the next big challenge. If your software has the power to fly a multi-ton aircraft, then that code has to be just as strong, just as reliable as a physical part of the wing. It's not just software anymore. It has to be treated like a critical piece of the plane's structure.
And this is how the industry makes sure the code is strong enough. It's a standard called DAL A. You can think of it as the official rulebook. It's this incredibly tough, incredibly detailed set of standards for how you have to design, write, and, most importantly, prove that your software is safe.
Now, this DAL A standard isn't a one-size-fits-all thing. It's broken down into these tiers, called design assurance levels. Way down at the bottom, you have level E, for something like the in-flight entertainment system. If it fails, it's annoying, but no big deal. But all the way at the top, that's level A. That's for the flight controls. A failure there is defined as catastrophic. The standards are just astronomical, because failure is quite literally not an option.
So, how long does it take to get that level A seal of approval? For a single, critical software component, the process of verifying and certifying it can take anywhere from 1.5 years to 3 full years. That's the kind of intense scrutiny we're talking about.
But what happens when this incredibly complex system of philosophy, design, and verification, what happens when it breaks down? Well, the tragic story of the Boeing 737 MAX gives us a very stark, very real-world answer. The MCAS system on the 737 MAX was just a cascade of failures. First, you had a piece of software that was only supposed to be a small background helper, but it was given way too much authority over the plane's controls. Then, and this is critical, its design relied on information from just a single fault-prone sensor. And finally, the whole safety analysis process we just talked about, it completely underestimated the catastrophic risk of that single point of failure.
And that really brings us back to the most important point of all. When you look at the whole journey, from that wild F8 experiment to the deep philosophical split between Airbus and Boeing, all the way to the insane rigor of DO 178C, it all teaches us this one vital lesson. The millions of lines of code flying our planes aren't just a feature. They are the fundamental architecture of safety.
And all of this leaves us with a huge question for the future. As we rely more and more on software, as we start bringing AI into the cockpit, the challenge isn't just about making the code smarter. It's about making it wise. It's about building in a deeper kind of wisdom that knows how to anticipate, how to adapt, and above all else, how to protect.